So next up, someone I've lost many games of Settlers of Catan to, Jake Keuhlen.
Thanks, Amatosh. Probably the best distinction I could get, actually. That's great. Yeah, so I think I'm the last talk for tonight. So I get the distinction of being flexible on time. Maybe we'll get out of here a little bit early, maybe not. We'll see how many questions people have. But tonight I'm going to talk about practical STM. So one of the things that I found when I was learning Haskell is it's like really hard to find real-world examples of complex Haskell things. And STM for me was, for a long time, very opaque. It's like really hard to get started with. That's what it felt like. But I don't think that's actually the reality of it. And so hopefully at the end of this talk, you'll be able to walk away realizing that it's a tool that you can use, and it's a relatively simple tool once you know what to reach for. So I'm going to kind of talk through a motivating example, because that's the way that I like to think through solving problems is, why am I going to use this tool? It's really a tool in like a programmer's tool belt. When should I reach for this tool? So in general, most people who have done programming for a little while could recognize this general pattern that computation often needs to be delayed or deferred for some reason. One example is maybe you have an HTTP request and you have a user waiting on the other side of that, but this computation is going to take on the order of like 10 minutes to complete. And obviously, HTTP is not going to stay open for that long, so you need to kind of like defer computation for a little bit, respond to the user right away, and process this thing later. Maybe you need to do batch computations, so you want to kind of group together every 10 requests and do something with that. And for one reason of that, maybe it's because every time you call some partner API, it costs you money. And so you want to group those and only do it once per day to kind of save on cost for calling some other partner API. So these are all like situations where you will probably need concurrency to some degree to solve these problems in a scalable way. And this is exactly where STM is going to come in. But before we get to that, I'm going to kind of take a little bit of a detour and talk a little bit about concurrency primitives. So I think there are 3 primitives that a lot of people will hear. If you take a computer science concurrency class, you're going to walk away hating these 3 words: lock, mutex, and semaphore. So very, very simply, locks are a way to ensure that a single thread is the only thing that can access a chunk of memory. A mutex is the same thing. It's a system-wide lock where multiple processes are restricted on accessing that same memory rather than just threads of a single process. And then a semaphore is kind of a constrained mutex that says, maybe I want only 2 threads to touch this shared region of memory. And why am I talking about semaphore in a Haskell talk? I kind of have 3 reasons for this. So one, STM is not Haskell specific. We're going to talk about that, but you can walk away with this and then go look for STM in basically any mainstream language has the implementations of STM today. Haskell is great because the type system allows for additional safety guarantees, but this is a tool that exists in all programmers' belts, not just Haskell specific. Second is that a lot of the multi-threading strategies that you're going to encounter of like, how do I deal with solving locks or race conditions, they're useful for solving a variety of problems, and they're useful in conjunction with STM in many cases as well. And then third is just STM isn't a panacea. You kind of need to know the basics of the industry around how do I do concurrent programming. And in fact, similarly, there's a version of STM that is specifically for semaphores, right? If you know what a semaphore is and when to use it, and you know what STM is and when to use it, you might stumble across that situation where you actually want the best of both worlds and find the tsem library on Hackage. All right, so with that out of the way, we're going to talk about STM. And this first sentence is probably the simplest way I can think of to describe STM, and I kind of think of it as STM provides a way to have data which threads can transactionally access. And it's very specific language, and I think the important part there is about transactions first. So I stole this from a paper that I found, and I liked their description of transaction here. So a transaction is a finite sequence of local and shared memory machine instructions. That sounds very complicated. Basically, it means we get to write in transactions and we get to read in transactions, and that's it. Very simple. But the important part is that a transaction can either fail or complete successfully, but there's nothing else in between. You don't get partial success or partial failure. It is always either a full success or a full failure that's visible atomically to other processes. And that's another very specific and intentional word. And atomically is really, really important. You're going to see it so much that it's actually the name of one of the most important functions in the STM library. Funnily enough, I think the best definition of transaction atomicity that I've ever read is from a databases book, on which multi-threaded atomicity is not the same as database, like ACID state. atomicity, but Martin Kleppelin defines it in designing data-intensive applications as if one thread executes an atomic operation, that means there's no way that another thread could see the half-finished result of the operation. The system can only be in the state it was before the operation or after the operation, not something in between. That's like a really, really important important concept around STM, because you know that each of these pieces just can't be half finished. And that's going to come up on kind of again as you're using it. But if you start thinking about this in terms of Haskell types, you think of atomically as something that moves us from a specific STM context into a larger I/O context in a single uninterruptible step. So atomically is kind of a type from STMA to IOA. So STM is great. People know that. If you've been in Haskell, you've read random things, you probably can just say like, oh yeah, STM is great. I've never used it, but that's like a thing that I've heard and read. But the why is always like somewhat hard to explain. And people will just say like composability. Like composition, composability, that's a thing that like functional programmers say. It came up in Mitchell's talk earlier, right? Like it's just a thing that we talk about. But what does it mean? And in this case with STM specifically, it means you can take two random pieces of STM code, combine them together, and get a new single function that does not have risk of deadlock within it. So a function A of type STMA, a function B of STMA, and then I can create function C, which is just monadically binding those two things together, has a guarantee that that code will not deadlock when you run it in an atomic action. That's kind of the entirety of why STM is amazing, and it's very different from other languages. So when I was looking for more examples here, I found this great Stack Overflow post where they just write simple code both in Java using Java's synchronized primitive and Haskell code using TM-vars, or sorry, just T-vars here. And you can kind of think about like withdrawing and transferring from some kind of an account, and you can write two synchronized thread things for depositing money or withdrawing money and then transferring money, but that transfer is not atomic in Java synchronization with basic non-STM tools. So you can run into race conditions where you can withdraw money and deposit, or if the withdrawal fails, you actually can't deposit on other threads, and you can get race conditions between that when you run that transfer action in multiple threads. In Haskell, however, if the withdrawal fails for any reason, then the whole block just is undone, and you don't end up with some kind of locking or deadlocking possibility between those operations. All right, so going back to my motivating example, we're gonna get a little bit more specific. So let's say that I'm running a garden center with some plant delivery business. I'm gonna call it Bullmoose Garden Center. So I never wanna deal with a computer again. I'm like really sick of programming, and so I start this delivery business, but I'm doing it all old school. You have to call me, and I'm going to write down your order on like a notepad, and then I'm going to put my phone down and go away and like deliver these orders. So when someone calls, I just write it down on my notepad, and if you call when I'm not there, sucks to be you, call back tomorrow. I don't have voicemail. It's like a very, very simple, single-threaded process. And it's so simple as a single-threaded process, you can write Haskell code that represents this exact thing. So this is very simple. It's just a recursive function. There's no STM here. All it is command line just waiting for me to type in an order. And then if I type the word deliver, then I get the list of things to deliver. And then the whole thread just dies, and you have to wait for me to start the process again for me to write something. This is like a really simple process. And single-threaded programming can always almost be this simple. But as soon as you expand, maybe my business is growing, and so I need to hire a dedicated delivery driver. Now I've got two processes running, and I need to kind of coordinate between them in some slightly more complicated way. And the more complex way can also include the basics of concurrency that we've been talking about. And this is where you can bring in STM to write an example that does all of the things we're going to want to do for a delivery business without causing any deadlocks. So adding more complexity here, we're going to need to create some kind of communication channel for whoever's on the phones taking orders and whoever's doing the delivery. So the first piece of STM code that you're actually going to see here is called a TM-var. And a TM-var, when you think about it, it's just a thread synchronized box. And a box can either be empty or it can have something in it, but that's it. And TM-var is parameterized by some type function, or by type variable A. In this case, we'll have a list of strings that go into it, of just like a list of all of the things that have been ordered that we need to deliver. So when you act on a TM-var, you can just put something into it, and there's already something there. The thread will wait until it can add something to it. or it will try and read from the, or take something from the box, and if there's nothing there, it will wait until there is something in the box before the thread can do anything. So in this case, we do something really simple. We create a new box, we kind of put an empty list into it to start with, and then we start one worker thread that just runs forever trying to do deliveries. And the deliveries are relatively simple. You know, take a nap between deliveries, and then go look at the list and grab whatever's there, put back an empty list so that there's something else to write on for whoever's taking orders, and then deliver all of those orders. And when you take orders, you just kind of take from the TM var, you take that list out of the box, shove something onto the front of it, and then put it back in the box for a delivery driver who may want it. And this works. You can run the code in GHDI, and you can kind of see as an example, maybe we start off, we didn't take any orders, the delivery didn't do anything, and then you start typing things in, and the delivery driver will pick it up. You can just keep typing, and the delivery will run in the background, and just keep pulling off all of the things and putting back a new list. And again, running without any risk of deadlocks or problems between the threads. All right, so I want to go aside for just 1 second and point out this code, which is kind of like what I wrote before, but this time I kind of forgot a very important piece of code. So this part looks very, very similar to the previous version, but there's just one line missing, and that line will cause the fork thread to deadlock. When you try and run that program with this version, GHC is pretty amazing, and it will detect that that deadlock happened during the runtime, kill the thread, and then give you an incredibly helpful error message that looks like this. It doesn't look like much, but this is so much better than any concurrent language I've ever had when things just hang and you had no idea that the thread even was hanging, and you're like, why are my job's not getting picked up? And then you spend hours and hours trying to chase that down. This error message alone has probably saved me dozens of hours of debugging. And it's not special, it's not much, but it's extremely helpful because you can really understand it. And the reason that caused it in that previous example is that kind of forgot that one line, which is just atomically put something into the box. This is like a really common bug that I think of when I write STM code, because the type signature of a TM var is just like A. It's not like a maybe that we would use in other places. It's just something that's in the box or not, but the presence of something in the box isn't expressed at the type level. And so when I add something like a list, which has some empty state and the empty box, I always forget to add this. And then the first time I run it, I get that error message and realized, oh yeah, I need to put something in the box in the first place. Okay, so let's say that my garden center explodes into a garden empire, and thousands of orders and deliveries are happening per day, spread across dozens of workers now. So there's a couple of important things to note when you get to a business of this size, with multiple workers who are delivering orders and multiple workers who are taking orders. So first off, I want to make sure that no order is fulfilled more than once, right? You don't want to be sending extra product to people. Second, I want to be sure that every order that you receive is recorded quickly. You don't want people on the phones with customers who can't write down the order anywhere. So you want to make sure that you move through it quickly. You can't have two people fighting over that order list and stuck because they're both pulling back and forth saying, I want to write down my order first. And then third, same thing, you don't want that to happen with delivery drivers who can't get the list to then go do a delivery. So you need something that's another way to synchronize between many, many threads at the same time. And STM, again, has all of the tools that we need to do this kind of concurrent programming. So in this case, we're going to bring in a different type of STM variable, this called a TQ. So TQ is just a standard representation that you might see in any data science textbook of a FIFO queue. It's under the hood, it's represented with two linked lists, just like anything you might implement in a data structures class. And it's really, really simple. And it works great for all of these kinds of applications because you can kind of just put an order onto it, and the first one that goes in, the next delivery is going to pick it up right away. So in this case, we do something simple. We instantiate that new queue, and the queue just starts off empty. You don't have to do anything else there like we did with the tvar. And then I'm going to spawn a bunch of worker threads that are going to be doing the deliveries, and then I'll also spawn a bunch of threads taking orders. And in this case, we do something a little bit different where we will go through and just take random stutters so you can make sure there's really no deadlocks in here. You can play with this a bunch of times and you'll never actually encounter one, no matter the randomization. There's no race conditions, but you can play with it and prove that to yourself too, just experimentally. So our delivery just go through, they will read the first thing off of the queue, and then they'll go deliver it. And when you're taking orders, you kind of just grab a random order and just write it to the queue. And again, you run it, everything works great. There's never going to be a deadlock because it's just really that easy to add STM code and run it operationally. So one thing I will add is that normal things that come up in concurrent programming still happen when you do STM. So in this case, if we go back to this code, you'll see that I'm just like printing to std out, but I have 15 threads that are touching std out at any given point in time. So when you do that, you get messages in std out that look like this. It's a shared resource that you want to restrict access to. And there's a really, really simple way to do this. So much so that I didn't even consciously think that that's what I was doing when I was writing the code for this talk, because it's just like such an easy tool to reach for. So all I did was I created this new delivery log access, which is just a TM var with nothing in it, just unit, because what's in it doesn't matter. All I care about is just the shared controlled synchronization primitive. And then it's just 2 extra lines around my printing. One to just take out of the box so no one else can do anything, print to std out, and then atomically just put nothing back in the box so the next thread can go. And those 2 lines are, well, 2 lines around the print and then maybe just a helper function is all it takes to get messages that look a lot nicer. And you have the nice version of printing that looks back like this instead of having everything interleaved and impossible to read. Okay, so let's do the exact same example of this garden empire, but I want to do it again with showcasing the composability that I said was so great. Because so far we haven't really done much other than use the basics of STM. But there's another place which, like I said, the reason this is actually so great is not just the simplicity of using it, it's the composability of operators inside of STM. So we're going to set up a little bit of a different situation here, in that we're going to have still the same delivery threads, the same work, like order taking threads, but we're going to have another thread that kind of just helps out wherever is needed around the shop. Sometimes they'll take orders, sometimes they'll go out and run deliveries, depending on if there's things in the queue or not. So again, setup is pretty simple. We're going to create that delivery log access here just for making sure that the printing is really easy. We'll do similar things with delivery and taking orders, but I've kind of broken out the base actions in STM here into their own functions that you can see are in the STM monad. And then we're going to write this new thing, which is deliver or take orders STM, which is just a combination of those 2 things tagged together with the or else that comes from STM library. This or else is really cool because it's built around a catch retry. And so if the first operation tries to retry because it's blocked, it'll just move on to the second one before retrying the whole block again. In this case, that's all I had to do is just combine them, compose them in a way that gives you an STM thing. And I can guarantee that between delivering and taking orders, I'll still never have a race condition, even with multiple threads running this code all day long. So deliver or take orders is the IO action of this. Same kind of thing. We're just going to sleep randomly between things that we're doing to prove that there's no race conditions here. We'll go ahead and just keep running that atomically and still logging the output that we were doing, like the normal delivery threads. And again, it works. You can see, immediately we'll get the dahlias that are only coming from this thread as instead of the hard-coded list from the other ones. And everything kind of continues on nicely. So this is a really hopefully a practical example of STM and what it looks like. If you're interested in the paper behind STM and the implementation in Haskell, I'd highly recommend Composable Memory Transactions. This is kind of the inaugural paper that corresponded with the launch of the STM library. And it's fairly approachable in terms of academic papers. It's pretty easy to read, understand the motivations behind it. And if you're the type of person who likes academic papers, it's a great one to learn more about STM. And yeah, I'll have all the content here in blog post form up on my blog probably this weekend. So, any questions? Yeah.
For this workload, having perfect first in, first out semantics doesn't matter that much.
Yep.
Right? And so I was, with a TQ, there's those 2 points of contention, when you're adding something to it and when you're taking something off. And
yep.
If you have more than 10 to 20 cores trying to hit those, you will basically end up, you'll see scalability will flatten out for this kind of queue implementation. So I would wonder about an approach where you have more TQs and you're doing random sampling between them.
Yeah. All of the things that I showcase here are easily scalable to situations just like that. So we have a job queue that we use internally at Mercury that's actually built around Postgres being our persistence layer rather than an in-memory queue. That has scaled very, very well for us. I think we have 50 worker threads that are pulling from it constantly. And it's pretty easy to do. You can add more queues. You can pick between the queues. You can have randomization and sampling. You can do things like add priority to the queue instead of a FIFO queue. It's pretty easy to extend any part of this because the hard part in most systems when you're building this is actually just the concurrency. It's not the what do I want to do with the ordering of how should I process jobs and how often should I process them and which ones are most important. Do you have a question?
Yeah, I feel like when I learned about STM, there was a concern that short transactions could essentially deny service from longer transactions. Is this something you've run into? Is that still a thing?
Yeah, so I mean that is you'll hear it called like job queue starvation, and it's always a possibility. But then it gets back to like the prioritization of how do you want to define the rules around what gets picked up next. So some places you can do like a stutter around. I don't want the only things that will be short-lived. I want to make sure that we're also picking up things that are older, and just kind of like adding some randomization around that can help prevent those issues. But they're there, but it depends on the size of your job queue, whether or not it actually is really matters in practice. For us, we don't need that right now, but it's a possibility. We've talked about it internally for our own systems, and it's something you keep an eye on it and change it if you need to. But for the most part, it's not an issue. Yeah.
What's the easiest way to see a rate of rollbacks that are happening? Obviously, we'll talk about when there's a conflict there, STM will do.
Yeah.
Well, is there good analytics? I wasn't able to find it when I worked on the project.
So it's going to you could write it yourself if you really were curious about how often you're retrying. All of the primitives like reading or writing from a TM-var, a T-var, a TQ, TVQ, like whatever of the STM primitives that you're using, all of those operations, you can write them all yourself with the basics in the library. You can just like go look at the package source code, copy and paste it, and then add whatever you want for tracking. One of the things that I didn't talk about in any of these slides is that STM is actually really cool. Again, this is like the GHC runtime optimizing around STM, is that you typically do not retry unless the TVAR, for instance, has actually changed value. So if you go check for the box and it's empty and you're trying to pull out of it, the thread that did that action will not retry until the STM memory location has actually been updated. So GHC is really good at optimizing that. I've never had issues with retries running forever or spinning threads or something, specifically because of that runtime optimization that's built into GHC. One of the things that I have that didn't make to the talk that's in the written version is that STM code is very easy to understand for humans, but it's also really easy to understand for machines, which is why we get all of these really cool optimizations in GHC in the runtime, so that you don't have to worry about threads just spinning forever trying to check if a box gets pulled, and why if you have a deadlock, GHC can detect it and tell you about it. Yeah, Jack?
So speaking of retry, transaction sometimes you maybe need to do a side effect in the middle of your STM transaction.
Yeah.
Ideally shouldn't, right? So because it might retry and you do the side effect twice. But sometimes it can be kind of difficult to avoid that. So do you have any general recommendations as to how to
Yeah. So
do side effects?
this code is a good example of it, in which you're going to have the STM and the concurrency primitives in their own functions doing whatever you need them to do, and then you bring them into I/O in smaller chunks or smaller blocks. Any of the I/O blocks here are not composable, and you can create deadlocks by accidentally composing I/O, but when you're composing the STM, you're guaranteed that they won't. When you want to mix in side effects, some people get tempted, even for tracing logs, you might want to try inside of an atomically block, do trace M or unsafe perform I/O. If you do that, you basically break STM because there's a lot of things under the hood where, it's not good. So you really don't have the option to have an escape hatch out of STM if you want to run correctly. And so the best way to do it is to design your operations in those individual atomic blocks, and then do whatever side effect you need to do, and then put in the next block afterwards. So sometimes it requires restructuring the system to account for when do I need the concurrency and when do I need these other side effects. But yeah, you really can't actually do any I/O inside of an atomic action because STM just won't work correctly. You lose all of the compilation guarantees, and I think sometimes it can lead to non-determinism. It gets fun.
One cool one I've seen at Mercury is people creating STM actions that return
Yep. Yeah, you can definitely do continuation passing style of just like passing a side effect back and running that then, definitely. Yeah, Rob?
I actually was going to ask something related to that, but in a much stupider, smaller way. I noticed that, like, yeah, you're using like a number of atomically
Yep.
lines within an IO block, and for the most part, it's like there's one critical one that like does the thing that you care about, and the others are mostly manipulation of TM bars. I was going to ask, are TM bars like inherently unsafe in some way that you need to make accessing them atomic, or is they used atomically in that context just to go into STM?
Atomically is the only way to go from STM to IO. So that's your run monad to like get out of it and actually use it in the functions. But
Using like an M bar, if it's called, that would like be atomic in itself in IO.
yeah,
You just wouldn't get any of the STM benefits.
right, exactly. So mvar is just like mutable, shareable, it's like IOREF, kind of like shared state that way. And TMVAR is what gives you these concurrency, synchronous, like thread synchronization primitives. But you will notice that, you know, even around my, let's see, do I have it on this slide? Let's go back. So like looking at this log, so you have atomically before, you've got some side effect action, and then atomically afterwards. This code can actually lead to deadlocks in production, because if that, you know, std out disappears and this, you know, put string line fails, then you can end up in a condition where you have threads that are now deadlocked because of some other exception. So you're not like guaranteed, like I said, STM is not a panacea that all of your code will never deadlock and will be perfect, but it lets you reason about it, you know, in addition. But you're still, there's dangerous things that can happen whenever you do a side effect, and those things can kill a thread that, you know, otherwise didn't have like some self-healing action.
You could model this as a queue and another thread pulling from that queue without possibility of.
Yeah. Yep. Yeah, Evan?
Or I guess like you're acquiring and releasing a resource, so you can put it in a bracket.
You can do things like that, but you know, if the whole thread dies, like bracket doesn't help you that much, especially like if it is really like killed. Like if someone comes in and kill -9 on the, you know, specific process ID, like the thread's just gone. And so bracket, you know, other things like there are Haskell tools that help make it more safe, but you never have total control over your threads. Like someone just pulls the power cord, like your server is going down in a weird state. So, do you have a question?
I just wonder if there's a relationship between the ST monad and STM. You know, ST is kind of for like hiding IO actions in a way, or mutating state without the rest of the program being able to observe it. It seems like STM could either replace that or subsume it.
You could do those things, but they're very different in intention of when you would apply them. But there's lots of overlap between, you might actually want to use ST in combination with STM. To the question that Jack asked earlier around like aggregating IO or like other side effects, people will use like writer monad in addition to STM to like collect a bunch of things that you want to have happen right after the resource is unlocked, and then do, you know, carry out those actions. And you can do a similar thing with like ST and other state monads. Yeah. Any other questions? All right.